pleasure as Director of the UCL-Energy Institute to welcome you all to this evening's seminar. Thank you all for coming on what is probably the hottest day of the year so far. But it's my great pleasure to introduce Mark Barrett, who is at the UCL-Energy Institute today. And Mark has probably spent longer than anybody else in the UK running and creating different energy systems models, and so has a unique perspective, I think, on the sort of modelling of the UK energy system. And I think a classic example of the situation where the modeller is often more important than the model, I think. So it's my great pleasure to introduce Mark. Just to tell you the format, so it's a 45-minute presentation. There'll be 15 minutes of Q&A, followed by drinks upstairs and further discussion. And Mark will be around this evening for any further questions then as well. Thank you.
Thanks, Taj. Yep, I'll be here for the free drinks. Tonight, there's going to be some levity, but we're going to talk about feeding the Leviathan. And Leviathan goes right back into mythology as a giant sea creature and was taken up by the Jewish faith, for example. But in particular, in 1651, Thomas Hobbes is one of the first kind of social philosophers who included a sort of physical part about human nature and the evolution of society. And he was, amongst other things, responsible for the quote of "life is nasty, brutish and short." But his idea was that just as cells form bodies, so bodies form society in these big interacting and coherent organisms. And so he says, for by art is created that great Leviathan, which is but an artificial man, in which the sovereignty is an artificial soul. And by soul, I think here he means the governance of this, in terms of the collective governance, giving life and motion to the whole body. And what is particularly interesting about him, Newton was about 10 when he wrote this, is that talking about the instincts of people and looking more at an evolutionary perspective, which of course has taken up in recent times. So, as a bonus, I'm not going to start at Mort AD, but 3.5 billion years ago, to about 1 billion years after the Earth formed, and we had the evolution of environment and energy in the world, the rotation of the Earth and the climate forming, and actually there's a lot of atmospheric development at this time. So the first atmospheric crisis or environmental crisis was when photosynthesis started happening and oxygen levels went up. And oxygen is actually very poisonous if you don't have the systems to cope with it. So basically the rotation of the Earth and it's going around its orbit, we have these, so we have energy in the Earth's environment, and the largest input is solar energy, and that secondary causes wind, which in turn causes waves, all of which we can harness, and tides due to the motion of the Earth, the Moon, and the Sun, and radioactivity, which is the leftovers from stellar evolution. And then about 3.5 billion years ago, we got the rise of the replicators. So we had chemical systems which harnessed high-grade energy, in the end solar energy, and through a cycle using this high-grade energy to reproduce information. So you've got these replicating systems. And for about a couple of billion years, these replicating systems solely consisted of microbes, single-celled organisms. And then relatively late in the evolution, we got plants, which harness the sun directly, and then animals, which fed off the plants. And to note that fossil fuels and biology are simply dead replicators. And this went on for, life probably started around 3.5 billion years ago, and this went on for about 3.499 billion years. And then we got us. Evolving, perhaps a million years ago, you can identify them as Homo sapiens. It's not exactly clear when it happens. And so we have these marvelous creatures here, which have an energy supply of about 130 watts. And they're taking oxygen. The energy is in the form of reduced carbon and carbohydrates and so forth. And so you burn the carbohydrates and oxygen and you release carbon dioxide. To cope with the varying diurnal and seasonal availability of energy, animals have storage. So biblical evidence suggests that the storage is about 40 days. Some, like me, is probably 50 or 60. But then we also have shorter term stores in our body for storing glycogen and various chemicals for shorter terms, like if you start running or something, then it will rapidly make that energy available. In order to manage demand across time, the creatures have marvelous adaptive envelopes, so that when it's cold, they reduce blood flow from the envelope to reduce heat losses. When it's hot, they'll increase blood flow to increase heat losses, to keep a constant temperature. About 20% of this 130 watts goes into these smart control systems here, which of course most of our energy control is autonomic. We're not aware of changes in blood flow. But on a larger scale, of course, we use these smart control systems to go out and find energy, i.e. food and environment. And then about 10,000 years ago, rather than just chasing around where the berries were, or the animals, the mammoths or whatever they're going to eat, they started developing exosomatic technologies outside their bodies. And 10,000 years ago, they started domesticating plants and animals. So that rather than having to chase through the environment to find energy, they started growing it with these agricultural technologies and storing it also. And so this went on, and there are a few millions, tens of millions. We don't really know what the population was over a period of time. So it's talked about agriculture, and they're still developing on renewable energy. Here's our population here. Then around this period, we discovered the dead replicators. We discovered coal, oil and gas. And at about the same time, we got this fantastic increase in population. So if you look on a long time scale, it's bimbling along here, a few tens, hundreds of millions of people, mostly in China, and then bang.
Can you read the date when it starts rising? I can't read it.
Right, sorry. Yeah, so, well, this is about 1850. That's at 1800 there. So we started using coal, oil and gas. Well, of course, the Chinese, etc., used little bits. But the great exploitation of coal, oil and gas started in 1600, and then going into the Industrial Revolution here. And so you've got this vast increase in energy consumption here, this great big peak, and this great population increase. Part of the reason for population increase, of course, is this exploitation of energy, particularly for agricultural systems, but also in terms of clean water supply, better food supply, all these different reasons. So when we look on this kind of timescale from 0 to 2500 AD, then you can see there's this kind of finite fuel, dead replicated blip of consumption. And we know it can't go on too long because there's only so much stuff in the ground. It has to stop at some time. The projection for population is to peak maybe around 9, 10, 11 billion later in this century. We don't really know what will happen there because it depends on human behaviour, of course. And so going into the longer term, there may be actually a reduction in human population. The birth rates and populations will start declining in the richer countries from the next 10 or 20 years. One of population forecast I saw for Japan is 15 people in 2300. Speculative, of course. And so as we go into this future, however many people there are, we know that we're going to have to go on to a renewable energy diet. And so I think this is quite an interesting picture. We have this sort of evolution of Leviathan over this kind of period, and maybe we're going to go towards a sort of steady state period for the world. Whether that's bearable psychologically, because we always need new challenges, etc. Perhaps we'll just be writing lots of plays and composing operas or something, I don't know. So we've got this great expansion in the use of dead replicators, plus a little bit of nuclear energy. And so we now have a physiology of Leviathan. And I'm sure you can't read this, I don't think I can. But basically we have these different organs, if you like, of Leviathan here. So we still have the people here, about 7 billion of them. And they, of course, need to be fed with biomass coming in here. In the UK, this biomass supply is about 7 gigawatts. That's 7 big power stations providing food. Then we have where we spend about 85% of our time in the UK, in our homes, and in the service sectors, in non-domestic buildings, universities, offices, etc. Then we have industry here. Then we have national transport here, so that's cars, railways, trucks, and so on. And then we have international transport with shipping and aviation. And over on the right-hand side here, we have our primary energy inputs into the physiology of Leviathan. So here we have gas in blue. This is the UK, by the way. And here we have our inputs of coal and oil. Here's our electricity system here. So we have renewables, tide, solar, hydro and wind here. We have gas generation there. We have solid, liquid and nuclear generation in here. These primary inputs then go through intermediate conversion and storage systems here. So if we take oil, for example, comes in, it's refined, crude oil is refined, through products, which then go into the transport subsectors. When we look at gas here, then of course that's mainly used for heating in dwellings, services and industry. And then we have our electricity system here coming through, and again that's supplying directly to these end-use sectors. No electricity goes into international transport for rather obvious reasons that the cables have to be too long. And what you're seeing here is the evolution in a particular scenario of Leviathan going through the years. So we're weaning ourselves off gas and oil here and going to electricity. When we look at this subsector here, this is providing heat and district heating to these subsectors. So heat inputs, we have, say, gas going into combined heat and power. We have biomass going into combined heat and power. And we also have any surplus electricity going to heat pumps into our district heating heat store here, and then on to sectors of use. In here, we're substituting for our fossil fuel oil using synthetic chemicals from like hydrogen and ammonia and biofuels coming in here to replace. So that's the basic sort of physiology of Leviathan. Then in addition to that, of course, we have to control it. So instead of a brain, we have a control system which controls the flows of energy, everything from your thermostat and time clock in your house, through to the control of the gas supply system, through to the scheduling of these power plants to provide electricity, so you meet the demand at every minute of the day. And in the control system, just like in the human body, we have sensors to detect the status of the environment and the demands. Then we have processing to make predictions, for example, of how much wind power there will be, or how much heat demand will be. And then we have actuators which actually send signals out to control and switch these things on and off. This, of course, is what is now called the smart grid. That's the term about this decade. There'll be another one next decade, no doubt. So, that's a sort of overview. So, we're going to look at two timescales. First of all, we're going to look at the evolution of this physiology over the next decades. And then later we will look at the short-term, short-time operation of this, minute to minute in a day. For looking at the long term, year by year, we're going to use this society, energy and environment model, scenario model, which tries to look at how the system might evolve over a period, in this case of 40 years to 2050, with the objectives of securely using renewable energy. As we've seen, that's ultimately where we have to go, and to reduce environmental risk, whether it's global warming, or acid rain, or air pollution and air quality in our cities. So the fundamental driver of energy system is us. So the first thing we want to look at is how many people are there, what sort of age structure and so on will they do, and what will they be doing? So first of all here, we have scenarios of population done by these are national population projections, they're not mine. And we see, given different, you have the stock of people, you add to the stock of people through birth and through immigration in a particular country, and you subtract the Grim Reaper and emigration. So you have a stock model of people. And here is a range of population projections made by the National Population Projections people. And we see that you might go from 65 million in 2050 to 90 million. And plainly, this has huge, huge impacts on demand. Everything else being equal, if we have that many people, we're going to have 50% more energy demand than if we have that many. And this is rarely discussed in detail in energy scenarios. Then I've taken here, this, we've built a demography and household model here, taking this kind of projection of about 70 million there, and typical fertility rates, immigration and emigration rates. We can then make a projection of the number of people, which is here, and how many are in each 5-year age band, so that's 0 to 5, 6 to 10, and so forth. And what we see, of course, is an increase in the people who are 60 to 80 years old. 60 to 110 years old, up here. So that's millions, sorry. And this is going up to 150, 110, and so on. Huge increase in the number of older people projected, of which I'm one. Then, coupled with that, is that as we age and as we get richer, we tend to live in smaller households. And in particular, here we have the number of households with only one person. And we can see it nearly doubles. It's partly age and so on, it's partly, I think, if you can afford it, you don't want to sit in a little box with somebody else, you live on your own. And this is increasingly common. This has big implications in the general. If you're in your living room and there's one of you, you'll use twice as much energy to heat that living room as if there's two of you per person. So as we go to smaller households, there'll be more energy per person. And then there's another question, is what kind of houses will we live in? So I've made a projection here, simply assuming, given this household structure, that we will live in the same kind of detached, semi-detached, terraced flats and residential homes as we do now. This might change quite radically again. Typically what happens is that a lot of older people, when their children leave home, they live on their own in great big houses and they use an awful lot of energy per person. When we want to look at over the next 40 years, we need to consider how fast things might change. And I've just given you some examples here of some of the stocks of people and technologies and their kind of lifetimes. So we have people here, which just discussed, around 80 years life, which is double the length of time to 2050. And that has implications for how much our behaviour might change. When we look at dwellings, maybe a lifetime of something like 100 years. So more than half, the vast majority of dwellings will still, that exist now, will still be there in 2100, in 2050. Next up, we have things like aircraft, ships and power stations, which might live 20, 30, 40, 50 years. And finally, we have the shorter term technologies like cars and refrigerators and appliances, which only last 50 years. So you can see if you introduce a new technology here, it'll very rapidly penetrate into the stock. Whereas for these, much, much slower. And this puts a limit on how fast we can easily change Leviathan's physiology. So in SEEScen, what we do is we look at 5 kinds of classes of measures that you can do to change the people and energy system. So there are behavioural measures here, speed reductions on motorways, effective comfort temperature in buildings by wearing sweaters, downsizing cars, demand management, modal change from car to bus and rail, and so forth. And they have what I'm going to call typically rates at which you can do it. Speed reductions on motorways are very fast, 5 years, whereas changing freight mode from truck to rail takes much longer. Then we have demand management measures. So this includes things like land use change, things like insulating buildings and ventilation control, demand management in non-residential sectors. So that's some technology coming now. And then we have a change in fuel mix, for example, from a shift to electric vehicles and renewables at end use, and in public supply shift to combined heat and power renewables. Then we have efficiency improvements of energy conversion, better boilers, better heat pumps, etc. And finally, end of pipe. These are all preventive measures. Then we have end of pipe. We've created this stuff. Now we're going to have to try and cure it with catalytic converters or hide it away with carbon sequestration. So we have all these different kinds of rates at which these measures can be implemented. And we can combine these in different ways. These decision variables, which represent our policies. So we have very fast acting decision variables, like speed on motorways, and then rather slow ones, like power stations and so forth. And so what we try and do is combine these decision variables, these policies, in different ways to see how fast we can balance these things to be able to reach the targets we want to reach in the time we want to reach them. So just a couple of examples now. One is going to be transport and behaviour and one on dwellings. An example of how important behaviour is. Within 15 years, if we chose small cars instead of the average car, it's about 1.4 litres, 1.5 litres, something like that, then you would reduce energy and carbon from cars by about 50% in 15 years. Simply by choosing a car which still has 5 seats, will do 80 miles an hour, but is just more efficient. Simple consumer choice. And it would reduce UK total emissions by about 7%. Of course, the general trend is that the car now that you buy would have been called a sports car 30 years ago. They're huge, they're heavy, and they're incredibly fast. I have a diesel Citroen, which is faster than a Mini Cooper when they originally came out, which was considered a hot car. Then, within 5 years, if you could enforce speed limits on motorways, that's just to stop people breaking the law, reduce energy emissions on motorways by about 15%, which would reduce UK total emissions by 1.5%, just by applying the law. Then, modal shift from oil to renewable electricity supplying vehicles and railways is an important option. for short journeys going to electric vehicles, for longer journeys going to electric one-ways, because they can use renewable electricity. And then finally, this is the toughest nut of all, is aviation. Aviation global warming impact can only really be leveled, let alone reduced, if you halve demand growth. There really are no big technical options for reducing aviation global warming by any quantity. If you have the very best engines, the very best fuselages, biofuels, etc., that'll buy you maybe 5 or 10 years of growth. So we can come up with a scenario to try to combine these things. And so the first thing we have is the load distance, how many passenger kilometres we travel. Most of the scenarios are like this. And when you actually think about what that means, continued growth is you're spending your whole time travelling. And in fact, there are real signs of saturation now. And so with this kind of behavioural thing, perhaps we can level off demand like this. And there are signs that there is saturation going around. If in addition to controlling the passenger demand, we make the modal shift to buses and trains and so forth, then the vehicle distance becomes even much lower. And of course these big vehicles, provided there's enough people in them, are much more efficient and reduces congestion and so forth. Such that when we combine all of these things, we can go down to very low levels just with behavioural measures, reducing the amount of delivered energy going into our transport system. If we just do technological means, we get onto this kind of profile, most efficient cars and so forth. If we combine technology and behaviour, we get down to the slowest profile for delivered energy there. So this is exploring different mixes of behavioural and technological measures in the transport sector.
What are the units on the graph, on the Y? PJ?
Petajoules is 10 to the 15 joules. Aviation global warming, just come back to that a little bit, because it's a really dismal topic. Because aircraft, when you burn chemical fuels in aircraft, kerosene or biofuels, doesn't matter, you produce oxides of nitrogen and water at high altitude. And these cause secondary global warming, not just the carbon dioxide, forming high altitude clouds, high altitude ozone, such that if you have 1 unit of the global warming from the carbon, you'll get another additional 1 or 2 units from the high altitude effects. And so even if you control aviation demand to half of its current level, then aviation might be contributing, this is now 1 million tonnes of carbon dioxide equivalent, it's a global warming impact of the emissions. Aviation will contribute about half of global warming in 2050.
If you control growth.
This includes some behavioural means where there's not so much demand growth. If you have demand growth, you'll be up here somewhere. So that's not to talk about that too much. An example now of rate of change of domestic energy of people and dwellings. So at the moment we have about 25 million households in these dwellings here, and they're coloured red because they're quite high energy users. If we demolish about 3% of them by 2050, this many existing houses remain. And then we have a refurbishment programme whereby unrefurbished and then we refurbish here in the green colour. And so we're refurbishing in this scenario 75% of dwellings by 2050. So that's about 20 million refurbishments, which is a huge, huge effort. And then on top of that, for the new households formed, we have to build these new dwellings here. So here we can see the sort of stock dynamics of people and households and dwellings and how that has to change. If we then make assumptions about the levels of insulation of refurbished dwellings and of new dwellings, then we get this profile for total heat demand for space and water heating in the dwelling stock. And what you notice here is that the new build really isn't going to save our skins. It's a small fraction of what the heat demand will be in 2050. So then if we combine similar studies for the different sectors, I don't have time to go through them all, for industry, for the service sector and so on, then we end up here with this scenario, which is maximum technology change, maximum behavioural change. Then we end up with this profile of deliveries by fuel. So a great increase in electricity, a great decrease in gas, biomass, sorry, this is actually district heating. But we still have quite a lot of liquid fuels, for example, to trucks, that's very difficult to substitute.
When you have CHP, what are the fuels of the CHP?
Well, there's a mix here, so we have gas, CHP, liquid and solid. But in the end, my belief is that most of it will be biomass.
They're complaining about air pollution in trucks and CHP right now.
Well,
preventing it being
if you go
approved.
if you go to Gothenburg or Stockholm, you will find district heating schemes with refuse and coal and waste oil and biomass, a whole mix of things. And with large plant like that, you can put on the very best emission control systems, particulates and volatiles. So there really isn't a problem when you go to Scandinavia. In fact, if you go to Scandinavia, you will see probably Scandinavia is probably about 2025. And then in this kind of extreme scenario, we end up with this shift from gas and oil and coal and nuclear to a predominantly wind and solar future of primary energy. This again is a maximum technology and behaviour. I mean, there's no such thing, of course, as maximum. You could choose to make your houses energy efficient for 20 years if you put enough effort in, and wall fitting if you like. So these things are all slightly arbitrary, and particularly with behavioural change. And then when we do this, if we look at the trade across the UK envelope, then up here is imports and down here is exports. So we've squandered our oil and gas, so we're coming up now as they diminish. Without this kind of scenario, then we're going to be importing a lot. In this particular scenario, what we find is that we have an excess of renewable energy, which we can export with Saudi Arabia and wind, but we're importing some liquid fuels, probably some gas, depends on the scenario, of course. The point is there that we might, A, reduce our total energy demand and our import requirement, but also we might be trading, exchanging energy rather than just importing. When we look at the economics of it, and this is even more uncertain, if we have a fairly high carbon scenario, this is what we're spending on demand management like insulation. That's what we're spending on conversion like wind turbines. And this is what we're spending on fuel. So in a high carbon scenario, we're spending a large proportion of our money on fuel. And of course, this is really unpredictable. So in a high carbon scenario, we have high unpredictable fuel costs and prices. We don't spend so much on capital, but it means our service cost, the cost of our heating our homes, is much less predictable because it depends on international fuel prices. Conversely, here we have a low energy scenario. We're spending much less on fuel here, just a bit for balancing and so forth. We're spending a lot more capital on conversion on our wind power and our solar PV units, and we're spending a lot more on demand management. But once we spend the capital, it's rather predictable. And so we have a more predictable service cost in the low carbon scenario. Which will cost the most? Here we have some scenarios with different combinations of behaviour and technological measures. And here we have the total cost of those scenarios. And this one here is the lowest carbon scenario. This one here is the cost of the low carbon scenario. Absolutely critical to the total cost of running the national energy system is what will the fossil fuel prices be? A few years ago, gas prices nearly tripled in this country. And nobody knows what the fuel prices will be. I'll just say I went along to a climate change committee scenarios for electricity, and one of the background things was fossil fuel prices for coal and gas, and the oil price on that day had a low price scenario, a medium, and a high price scenario for 2020. And on the day we were there, this is about 5 years ago, on the day we were there, the oil price was above the high scenario for 2020. So that's how unpredictable it is. And the other thing that's for sure is that the more carbon fuels we use, the higher the price of them will be. So the low carbon scenario means lower fuel prices.
Well, in these economic models, what's the implications of carbon cash flow? Because some of this is capital, as in upfront investment with later returns, and some of this is revenue, which is kind of money I've spent in.
Absolutely. I mean, this is a rather simple. What SEEScen does is it just adds up the capital costs, it annuitises them over the lifetimes of the technology, and given fuel price and operation maintenance.
Okay.
So it does give. So here, these are all annuitised costs for capital. So it doesn't actually give you a capital investment program.
Yeah. So there would be a real hump at the beginning of this in terms of capital investment.
Well, it just depends how fast you're building your wind turbines. And so forth. But this doesn't go into that amount of detail. This model was then applied to look at low emission scenarios for Europe. So we looked at 25 European countries and did 6 scenarios for each of the different combinations. And again, we have to start with the drivers. So here's the population forecast from about 2005 for Europe, peaking in around 2025. But the number of households to continue to increase for the reasons that I outlined earlier. And this is the GDP growth forecast. So again, forecasters beware. What's quite funny, I must say. So we tried different combinations of these. So here is a scenario for a 40% reduction in carbon by 2020 with new nuclear power stations, which reduce carbon emissions in Europe by about 7%. Here is a scenario now with maximum behavioural change. And I should say each of these strata is one of the 25, as then were, European countries. Then we tried a scenario with maximum technological change, no behavioural change, and no new nuclear. So you can see you get this long, as the technologies penetrate into the stocks, you get this long decline. And then we tried our maximum scenario, except no new nuclear, where we have maximum technology behaviour. And if you like, the avoided global warming is, let's say it carries on, is this area in here. That's the amount of carbon emission abatement as compared to a steady state in here. And when you add in behavioural change, your total carbon emission over the period is about a third less than with no behavioural change. And what is really critical is not the emissions, it's not the emissions of a particular year that matters. It's not even the total amount emitted over a period of time is important, but it's also the double integral of it. Because this bit of carbon here, because CO2 stays up in the atmosphere for a couple of hundred years, is warming all the way across there. Warming all the way across there. And so if you get a fast reduction, you get a much larger reduction in total global warming. And this is why behavioural measures are so important. If further we take into account that we might go to a tipping point, where if we don't go down a trajectory like this, but let's say we go on one like this, then around here we get runaway feedback with the methane coming out of the tundra, etc. So what we talk about there is the evolution of Leviathan over the period, well, most of the graph from 1990 to 2050. And it's quite easy to do. In a way, it's a sort of fancy accounting framework. Oh, let's have 50% nuclear, 50% wind. The question is, will these systems work? Now we have this system, we turn on the projector, somewhere down the line, a couple hundred miles away, a generator produces a little bit more power. So it's immediately responding to our needs. So we need to see whether it will actually work in engineering terms. And so for this, we're using this DynEMo, the dynamic energy model, which looks at the performance of the whole of Leviathan on periods of minutes and longer. So what are the temporal drivers of energy demand? Well, first of all, we have our friend the meteorology here, which is changing across winter, spring, summer, autumn, minute by minute, that's changing, but with some statistical reliability. Then we have the human use of time in the UK, which is actually quite invariable when you look at back to 1960, how much time we spend sleeping or relaxing or whatever, it changes very little. Because of course we're a diurnal mammal, and we've evolved in this way, and we ain't going to change in the very near future. But what we have done is we've developed this exosomatic apparatus here. We've developed this external skin, walls and windows and so forth. And so we have